Morning, thank you for coming to my conference. The aim of this presentation is to show how we can use large-scale assessment in mathematics education research. There are many critics towards LSA, large-scale assessment in mathematics education, and basically because they think there is only a behavioristic approach to the learning of mathematics without taking account the whole complexity of this phenomenon. And secondly, because in mathematics education we normally use qualitative methodologies and not so much the quantitative ones. But we believe that large-scale assessments have strong components that can help mathematics research. Basically, we use a very robust theoretical framework, a strong statistical framework, and we assess learning as a system in terms of an educational system, which has a lot of implications: educational, didactical, cognitive, cultural, political, and so on and so forth. And furthermore, large-scale assessment entangles several features which are also involved in mathematics education research. So we use theoretical frameworks, there are different methodologies, global and local analysis, context analysis, released items, microanalysis, and also other things, of course. And so why are we interested in using large-scale assessment and mathematics education research? So first of all, we need to have an analysis of the systemic behavior of our students from a more complex and wider perspective. And large-scale assessment brings new didactical phenomena that we need to interpret, and brings also solid findings, and so it brings a new strength to the epistemological foundation of mathematics education. And in our research in the group of Bolzano, directed by Giorgio Bolondi, we have outlined a new methodological block, which is structured along three schemes. We usually start with a qualitative analysis, which guides our research. Then we go through a quantitative analysis, and then we mix qualitative and quantitative analysis to answer our research questions. And so this methodology is sustained by a theoretical framework and a structured repository. Here in Italy it's called GenStil, and Federica Ferretti is the one who built it and designed it. And a very important aspect of large-scale assessment is the role played in outlining solid findings in mathematics education research. So first, we have very interesting data that confirm important results in mathematics education. And furthermore, we have the possibility to integrate and correlate different findings and different data to give a wider representation of what's going on in mathematics education. So now I want to bring a few examples. A very important example is the loss of meaning in algebra. And so we know from mathematics education that there is a loss of meaning of when you go from arithmetic to algebra, and typically in high school students start using symbols without relating them to any meaning, and basically to mathematical meaning. This is an example of a relationship of the behavior of a spring when you pull it, and how the spring elongates. And I'm not entering in details, but what is important is that the same test has been given to students of grade 8 and then students to grade 10, and these are the results. So the first regard grade 8, and we have, can you read it? Yes. It's more than 60% of correct answers, and when we go to high school, after 2 years of very strong training in symbolic algebra, the result collapses to less than 30%. So the use of large-scale assessment the use of large-scale assessment allows the quantification of the loss of meaning. This is a very important result. And there are many examples in literature starting from 1994 with Anna Svard and more recently with Louis Radford, from different aspects that have shown how critical it is when you go from arithmetics to algebra. And another very important result is that we can see that this phenomenon impacts also on medium and high-level students. So we would expect that as you go through the line of the competence curve, you would expect as the level of competence increases, students would behave better, or the curve, the line would drop. But in fact, we see that the wrong answers are chosen also at medium high-level students, and medium high-level competent students. And another important issue regards, if we look at mathematics education, mathematics learning as from a systemic point of view, it shows that there is a great gap between what we know from mathematics education and what actually happens in schools. And so we have to really rethink our teacher training and the teacher practices that we implement in schools. And our group and Federica and Giorgio Bolondi are doing a really important work in using INVALSI data for teacher training. Now I'll bring another example. This is our research we have conducted regarding inequalities. This is it's an example that is treated in thorough in high school. It's x squared plus 1 greater than 0, and it's very intuitive inequality, and the results are really astonishing. And we get 30% of correct answers, and I don't know if there are mathematics teachers, the amount of time and amount of training that students are exposed to in algebra, and in particular to equation and inequalities, and they can get it right. And again, if we look at the competence curve, we have wrong answers even at high level of competence. So this example has been given to 550,000 students. Numbers are really important to understand how strong this phenomenon can be. And the results refer to a sample of 27,000 students. And the correct answer is chosen by less than 40% of the students, and the structure D, even if it's totally senseless, it's chosen by 14% of the students, and the structures A and B by 19 and 23%, so what's overall it's another 40%, and I'll bring it back to. So it's A and B, it's x greater than 0 and x greater than -1, which tells us that students, they are looking for some kind of analogy between the original inequality and the possible solutions. And again, as I was saying before, even at high level of competences, there are these structures A and B are preferred by the students. So let's discuss this phenomenon. We have a macro phenomenon that emerges from the Italian educational system. So we would expect that the students would have at least done some kind of calculation. We call this attitudes pseudo-structural approach, when students use the symbols without really understanding the meaning, but at least a standard procedure that they have trained many times in school would have been chosen by the student, but it wasn't the case. And we see again a loss of mathematical meaning when there is a treatment operation. It means when you go from the symbolic register to another representation of the inequality in the symbolic register. And we see also a disembodiment of meaning in a very intuitive situation. What I'm trying to say, that you could solve this inequality just looking at, for instance, at the number line and put 1 and then seeing that you're just adding quantities which are greater than 0. So in a very embodied way you could understand that the solution is for all x, but the students don't do it. And another interesting result is that the INVALSI test, the way we are proposing the inequality, the fact the context is completely different from the one they're used to, and the fact that they have multiple choice and they don't have a blank sheet of paper in which they have to write, it somehow blocks the rituals they usually used to in school. So they don't carry out the calculation they have been trained to in school, but they do something else. And so another way to see this is that there is no didactical contract that they can attain to in order to solve the inequality. And so, as I was saying before, also the context is very important. So the multiple choice items and the structure of the structure of some kind unmasked the cognitive behavior behind the students' answers and the item and the structure they have chosen. So probably in a standard classroom they wouldn't have answered like this. And so the INVALSI test somehow breaks the usual structure of teacher, learning and students, which in mathematics education we call the Chevallard triangle. And so we need somehow a new conceptual framework to understand this systemic phenomenon. This is another example. It's research carried out regarding powers, still in high school, secondary high school, so it's 10th grade. And again, the students have a lot of training in this topic. And so this was the question. And these are the answers. So the correct answers are 30%. And the most chosen is the C, A to the power of 87. So they have just summed the exponents. So let's try and comment this. So again, a large sample of students have been tested with this question. Only a third were able to give the correct answer. And among the incorrect options, the most chosen is C, the one when we just sum the exponents. And again, as we go through the characteristic curve, you see that there is the wrong answer is given also at high levels of competence. So we see a disalignment of meaning between the personal meaning, so the way the students actually, the meaning that the students individually give to inequality, and the cultural meaning, which is the mathematical meaning we would like our students learn. And so again, a loss of meaning, again due to treatment. So we have the equation in the inequality in the symbolic language, and the representation of the inequality still in the symbolic language, but with another representation, puzzles the students. And so what happens is they're not able to frame appropriately in the context of power, thereby the student resorts to a well-known identity which doesn't fit in this context. So again, we have a pseudo-structural approach where students just manipulate symbols without understanding their meaning. And so what they're not able, the students are not able to factorize the powers in order to get the correct answer. And again, I want to underline, despite the thorough practice that students are exposed to in terms of treatment transformation. And another important result that this item shows is that the students are not able to distinguish between the signifiers and the signified. What happens, they identify the representation with the mathematical object, and this is the reason why they just sum the exponents, because they're not able to understand the meaning of the symbols and just use the symbol without any reference to the mathematical concept. And this is a very, very important solid finding, confirmation of a solid finding, which is called the cognitive paradox of Dual. I don't have time to explain it, but basically it's the students' mathematical objects are inaccessible, and so what students do is to identify the mathematical object with its representation. And the challenge in teaching and learning of mathematics is to allow students to make this distinction. So we are able to draw some conclusions. So what we are doing, what our research shows, is that we have identified a methodological block which is able to fulfill three very important criteria for mathematics education research. First, our results are coherent with results coming from previous researchers. Second, they highlight articulations of known results that have not been observed before. For instance, the example of the inequality is very important because our expectations in terms of mathematics education research would have been that at least the student would have performed the calculation resorting to rituals, resorting to the didactical contract, resorting to just the structure of the semiotic register, but they didn't do so. So this is really important result that large-scale assessment allowed us to highlight. And then they point out new phenomena that deserve further studies in order to be explained. A very important phenomenon that large-scale assessment shows is that difficulties that mathematics education research has outlined persist in high level in students with high levels of competence, and this is a research topic that needs further investigation. And so this is a validated methodological model that intertwines large-scale assessment and mathematics education paradigms. So I think, thank you very much for your attention.